All right, hello everyone. Welcome to another session on equilibrium. Now, so far we have learnt about the concept of reversibility, all reactions being reversible, and generally when we believe a reaction is over, we reach a point of equilibrium where it's happening in both directions, forward and backward at the same rate. We understood the concept of reversibility. We realized that the point of equilibrium could be arrived either from the reactant end or from the product end, and at equilibrium the amount of reactants and products would become constant with time. Much before that, we had seen the role of temperature affecting the rate of chemical reactions. You recall me talking about Arrhenius equation, then its logarithmic form. Then we derived the equation by which we proved that increase of temperature is always going to favor a reaction because it's going to increase the rate constant of the process. Now we were doing that for a reaction in one direction. Now naturally, with the concept of reversibility known, we'll want to see the role of temperature in equilibrium, how temperature is going to affect reactions which are reversible, how change of temperature is going to affect the yield of exothermic and endothermic reactions. So let's right away begin with that crude form of Arrhenius equation, then its logarithmic form, and the equation which we derived in the very first place. So certainly this is how it all began. K is equal to A into e to the power minus EA upon RT is how rate constant changes with temperature. This was activation energy, universal gas constant, exponential wala E, pre-exponential factor, and we used the logarithmic form which was log K is equal to log A minus EA upon 2.303 RT, 2.303 because we wanted to work with the common logarithm to the base 10. And at temperature T1, if the value was K1, at temperature T2, the value was K2. And we finally got this very important equation where at two different temperatures, the value of K could be written or obtained by this very popular equation. You know, this is going to solve so many questions where if the activation energy is known, I can calculate the rate constant at different temperatures. We realize that every time T2 is more than T1, if T2 is more than T1, then all of this positive because activation energy is never negative will mean K2 is more than K1, and for the same concentration of reactants, the rate of the reaction will increase. So temperature बढ़ाओगे, K बढ़ेगा, rate बढ़ेगा, temperature हमेशा एक process का rate बढ़ाएगा. टेम्परेचर बढ़ाने से रेट बढ़ेगा, ये बात मैथमेटिकली भी समझ में आती है. I tried to give you a logical approach as well. You recall me giving you the energy profile, that energy versus reaction plot. We'll talk of it, in this video right away. But one thing was clear. If you increase temperature increase in K. Temperature बढ़ेगा, K बढ़ेगा, rate बढ़ेगा. And now because I know reactions are reversible, reactants become product and product become reactants. For reactant becoming product, if the rate constant was some Kf, for backward reaction the rate constant is Kb. And now we want to see how temperature affects Kf as well as Kb. The energy profile which was bearing this look, reactant becoming product, and we were talking of this as the difference between the energy of reactant molecules and the activated complex. If this was the activation energy, now I believe it's happening both forward as well as backward. So this will look like EAF and this will look like EAB. Now reactant becoming product becoming reactant is a factual reality. So naturally, at some point, we'll know this is for an endothermic reaction. It will be a little different for an exothermic reaction. We'll go into all of that. But the two activation energies are different. And naturally, Kf and Kb will differ differently with change of temperature. Now we'll want to see how Kf changes if the values are Kf2 and Kf1 at two different temperatures, Kf1 at T1, Kf2 at T2. We'll naturally want to put EAF here, activation energy forward. And for the rate constant backward, I could write log Kb2 by Kb1, log Kb2 by Kb1 is equal to Ea. Now this is EAB T2 minus T1 upon 2.303 R T1 T2. So T1 temperature Kb1 value, at T2 value is Kb2. This is how Kf changes with temperature. This is how Kb changes with temperature. And in equilibrium, we will want to see how Kc changes with temperature. So we'll talk more about the energy profile when the time is right. You know about Kc in equilibrium. In equilibrium, for every reaction there is an equilibrium constant. That equilibrium constant Kc is the ratio of Kf and Kb. Now like Kf, Kb changes only on temperature, Kc changes only with temperature, Kc changes only with temperature. So at two different temperatures, T1, if it is Kc1, because this is Kf1 and this is Kb1, at temperature T2, when Kf becomes Kf2 and Kb becomes Kb2, naturally the ratio will become Kc2. And now we are interested in how Kc changes with temperature. We are interested in how Kc changes with temperature. Remember, higher the value of Kc, more is the yield of the product. Because this is the ratio of product upon reactant. In general, this is the reactant of product upon reactant. So a higher value of Kc will mean more product, higher the value of Kc, more is the yield of the process. If suppose I want to get Kc2 upon Kc1, which could be written as Kf2 upon Kb2 upon Kf1 upon Kb1, right away I'll want to rearrange it. And maybe write it as Kf2 upon Kf1 upon Kb2 upon Kb1. You could see that this could be rewritten in this manner. I'll just check if everything is there in the frame or not. Looks good. And very deliberately I am writing Kc2 upon Kc1, which initially is a ratio of this kind, in this manner, so that I can make use of these two equations. I can make use of these two equations. So to get Kc2 by Kc1, which is the ratio of this and this, let me call it equation 1, let me call it equation 2. And now if I do 1 minus 2, naturally log A minus log B is log A by B. And the way I have represented it there, you realize that 1 minus 2, if I call it equation 1, if I call it equation 2, then naturally 1 minus 2, which will be log of this upon log of this, will be eventually log of Kc2 upon Kc1, log of Kc2 upon Kc1. Now everything else remaining common, 1 minus 2 could be written as EAF minus EAB, T2 minus T1 upon 2.303 R T1 T2, which again can be written as log of Kc2 upon Kc1 is equal to delta H. Now this will be very important. This delta H thing will be very important. If you know a little bit of thermodynamics, this will not be new to you. Otherwise, this delta H is going to be a very important result. This is how K was changing with temperature. This is how Kc is changing with temperature. I'll quickly brief you about delta H. First of all, delta H is called enthalpy change of a process. You will know this term enthalpy more clearly in thermodynamics. For the time being, you can take enthalpy as the heat content, energy content of a set of molecules or system. So this is the change in heat content of a reaction, and naturally a change in chemical reaction would be the difference in the heat content of product and reactant. Final minus initial, product minus reactant. You will call it the enthalpy of product, enthalpy of reactant, energy content of product, energy content of reactant. And now suppose I draw an energy profile again. If I draw an energy profile again, see if this is how I draw an energy profile. If this is the heat content of the reactant, and if this is the heat content of the product, every time HP is more than HR, 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 it will mean delta H is positive, delta H is positive, and this will be an endothermic reaction. How do you know it's an endothermic reaction? When the product has higher energy content, when the product has higher energy content, certainly it would have absorbed energy, it would have absorbed energy. So HP more than HR, delta H positive, heat supplied, heat absorbed is an endothermic behavior. So this is the energy profile of an endothermic reaction. What's delta H? What's delta H? What's delta H is also the difference of EAF and EAB. This needs to be understood. What's delta H is also the difference of EAF and EAB. You know about activation energy forward, now you know about activation energy backward as well. So both in terms of value and sign, because here EAF is more than EAB, here EAF is more than EAB, EAF looks bigger than EAB, so naturally delta H will be positive. The look of an exothermic energy profile, the look of an exothermic energy profile will be the reverse. The look of the exothermic energy profile will be the reverse. And in an exothermic energy profile, which I want to draw here, product will have lower energy state than reactant. So if this is HP, heat content of product, and if this is HR, naturally this time delta H is equal to HP minus HR will be negative, this will be negative, and when it's negative, it's an exothermic reaction. Delta H negative is exothermic reaction. You will learn from the first principles of thermodynamics, heat released is negative. Heat released is negative. Every time product goes to a lower energy state, every time product goes to a lower energy state, this is also like conservation of energy. This is also like conservation of energy. If it goes to a lower energy state, naturally energy will be released. Energy will be released. Heat release is exothermic. This is the amount of delta H now, and this is negative because EAF you see is smaller than EAB. Here EAF is smaller than EAB. So EAF smaller than EAB, delta H negative. You will believe delta H is the difference of EAF and EAB. EAF more than EAB in endothermic, EAF more than EAB in endothermic, delta H is positive. EAF less than EAB, delta H negative, exothermic. Heat released is negative, heat absorbed is positive. Now certainly for endothermic and exothermic, it's only about time. With a little bit of maturity, you will also predict, you will also learn, you will also know that what's endothermic forward is exothermic backwards. What's endothermic forward is exothermic backwards. What's exothermic forward is endothermic backwards, naturally. And now the delta H values being different, we'll want to talk about some basic arithmetic first. With delta H, positive in one, negative in exothermic, if it's an endothermic reaction, where delta H is positive, you will claim if T2 is more than T1, all of this is positive, Kc2 is more than Kc1, and the yield will increase. If Kc increases, yield increases. So in endothermic reaction, when you increase temperature, rate forward increases, rate backward increases, and the yield also increases. Delta H positive, T2 more than T1, all positive will mean Kc2 more than Kc1. At a higher temperature, the yield will be higher. Whereas in an exothermic reaction, where delta H is negative, this time if T2 is more than T1, this negative, this positive will mean all of this is negative. Log of A by B negative will mean A is less than B. So this will mean that Kc2 is less than Kc1. So the yield will decrease. It's not good for the yield of the process. And this time, if you want Kc2 to be more than Kc1, this time in exothermic, if you want Kc2 to be more than Kc1, you will want T2 to be less than T1. You will want T2 to be less than T1 so that this negative and this negative eventually becomes positive. So that this negative and this negative eventually becomes positive. In a nutshell, what you cannot afford to forget is endothermic temperature should be high. Temperature should be high for more yield, and exothermic temperature should be low. Temperature should be low for more yield. So let's begin with a few facts which you'll want to get used to. All of chemistry, all of reversibility, equilibrium, endothermic, you'll want temperature to be high. Looks good, delta H positive, T2 more than T1, everything positive, Kc2 more than Kc1. Whereas exothermic, because this is negative, T2 more than T1 will make it negative, Kc2 will be less than Kc1. If T2 is less than T1, if you drop the temperature, if the temperature is lowered, final temperature is less than initial temperature, two negatives will become positive, and in exothermic temperature should be kept low. For more yield, here temperature should be high, exothermic temperature should be low. What is the catch? What is the catch? Temperature can never hurt a process. Temperature can never hurt a process. What's exothermic above? What exothermic forward is endothermic below. Still, I prefer to give you two different graphs. I again draw endothermic here. I again draw endothermic here. I again make you see that EAF is more than EAB. This is delta H, HRHP. This is an endothermic graph. This is from the first principles. Endothermic is heat absorbed, so naturally product का energy level ज़्यादा रहेगा. Exothermic is heat liberated. So heat liberated means it goes to a lower energy state. So what is the catch? Although you are supposed to remember, endothermic में temperature ज़्यादा रखने का, exothermic में temperature कम रखने का. What is the catch? And you will want to hear it very attentively. Temperature can never hurt a process. Temperature can never hurt a process. Realize when you write the basic equation involving two temperatures for the first time, you know, when we write log K2 by K1 is equal to E8 T2 minus T1 upon 2.303 R T1 T2 for the first time, you know, we did it in an earlier video. Temperature increase increases K, temperature increase increases K, and now you will want to listen very attentively. Different reactions will have different activation energies. Different reactions will have different activation energies. For two reactions having different activation energies, one having higher EA, will have a higher increase in K for the same change of temperature. From same T1 to same T2, the increase in K will be proportional to activation energy. For one reaction, activation energy is constant, so every time temperature is increased, K increases. For every reaction, activation energy is constant, so if T increases, K increases. But for two reactions having different activation energies, the increase in K will be more, for the reaction having higher EA. The increase in K will be more. I can write this equation again. So I am using this space again because this is a very vital statement. K increases more for a reaction having higher activation energy. This is such an important statement. Temperature always increases K. But the increase in K is more for a reaction having higher EA for certainly the same change of temperature. From same T1 to same T2. For the same change of temperature, a reaction having higher activation energy will have a higher increase in K. Now let's look at endothermic. EAF is more than EAB. So what happens in endothermic is KF increases, KB also increases, KF increases, KB also increases, but KF increases more than KB. because EAF is more than EAB, because EAF is more than EAB, KF2 upon KF1 is more than KB2 upon KB1. This is how you will want to know it. Because the increase in KF is more than the increase in KB, because the increase in KF is more than the increase in KB. From one equilibrium to another equilibrium, it will move forward. Temperature never hurts a process. Temperature always favors a process. Everything looks good in endothermic. रेट बढ़ेगा, यील्ड बढ़ेगा, क्योंकि इंडोथर्मिक में EAF EAB से ज़्यादा है. हम लोग अब दो रिएक्शन की बात नहीं कर रहे, हम लोग एक ही रिएक्शन की बात कर रहे हैं, जहाँ फॉरवर्ड एंडोथर्मिक है, बैकवर्ड एक्सोथर्मिक है. एंडोथर्मिक में टेम्परेचर ज़्यादा रहना चाहिए, एक्सोथर्मिक में टेम्परेचर कम रहना चाहिए. एंडोथर्मिक में EAF EAB से ज़्यादा है, KF KB से ज़्यादा बढ़ता है. रेट फॉरवर्ड इंक्रीजेज मोर देन रेट बैकवर्ड, एंड द न्यू इक्विलिब्रियम इज टू द राइट टुवर्ड्स द प्रोडक्ट, यील्ड इंक्रीजेज. यहाँ पर भी रेट नहीं घटता है, यहाँ पर भी रेट नहीं घटता है, यहाँ पर भी KF बढ़ता है, KB बढ़ता है, बट KB इंक्रीजेज मोर बिकॉज EAB इज मोर देन EF. इन एक्सोथर्मिक बिकॉज EAB is more than EAF, in exothermic because EAB is more than EAF, the increase in KB is more than that of KF. Here the increase in KB is more than that of KF. Here KB increases more than KF. Here KB increases more than KF. So rate forward increases, rate backward increases, rate forward increases, rate backward increases, but the increase in the rate of the backward reaction is more. The increase in the rate of the backward reaction is more. So यहाँ पे रेट बढ़ता है, KF भी बढ़ता है, KB भी बढ़ता है, बट KF से ज़्यादा KB बढ़ता है तो KC घट जाता है. रेट बढ़ता है बट यील्ड घट जाता है, रेट बढ़ता है बट यील्ड घट जाता है. तो हम लोग क्या करते हैं, हम लोग टेम्परेचर घटा देते हैं. टेम्परेचर घटाने से KF भी घटता है, KB भी घटता है. टेम्परेचर घटा देने से KF भी घटता है, KB भी घटता है. इस बार KB ज़्यादा घटता है बिकॉज द बैकवर्ड रिएक्शन इज हिंडर्ड मोर. ऑन डिक्रीजिंग टेम्परेचर दिस वाज द इंक्रीज इन KB. सिमिलरली ऑन डिक्रीजिंग टेम्परेचर द डिक्रीज इन KB इज मोर देन दैट ऑफ KF. This is what happens on increasing temperature. I don't want to confuse you. टेम्परेचर बढ़ाने से यहाँ पे KF भी बढ़ता है, KB भी बढ़ता है, बट द इंक्रीज इन KB इज मोर बिकॉज EAB इज मोर देन EAF. तो रेट बढ़ता है पर यील्ड घटता है. टेम्परेचर जब कम कर देते हो KF भी घटेगा, KB भी घटेगा, बट KB ज़्यादा घटेगा. और बिकॉज KB ज़्यादा घटेगा, नया इक्विलिब्रियम, फॉरवर्ड का भी रेट कम होगा, बैकवर्ड का भी रेट कम होगा. बैकवर्ड का रेट अगर ज़्यादा कम होगा मतलब नया इक्विलिब्रियम राइट में आएगा. बैकवर्ड अगर ज़्यादा हिट होगा तो फॉरवर्ड का यील्ड बढ़ जाएगा बट रेट घटेगा. यहाँ पर यील्ड बढ़ता है लेकिन रेट घटता है. और इसीलिए एक्सोथर्मिक में देयर इज दिस कंसेप्ट ऑफ ऑप्टिमम टेम्परेचर. जहाँ पे तुम यील्ड बढ़ाने के लिए टेम्परेचर बढ़ाते नहीं हो, बट टेम्परेचर उतना कम भी नहीं करते कि जिससे रेट बहुत कम हो जाए. आई थिंक आई हैव बीन एबल टू एक्सप्लेन ऑल ऑफ दिस बोथ मैथमेटिकली एंड ग्राफिकली. In exothermic, temperature should be low, not because temperature doesn't favor a process, but because in exothermic it favors the backward reaction more than the forward reaction. So you keep the temperature low, you compromise with the rate for the yield, but you do not keep it so low that the rate becomes very slow. So there we talk about an optimum temperature where the temperature will not be very high so that the yield is not very low. At the same time, the temperature is not very low so that the rate is not very low. So you want to keep it at a temperature where both the yield and the rate could be balanced. For endothermic, everything is all right. Rate बढ़ता है, yield भी बढ़ता है. So I think this will take care of all the questions which are problem solving as well as conceptual. Finally, we'll talk about catalyst. Remember, for the catalyst, at the same temperature, for the catalyst at the same temperature, you had an equation like this. For a catalyst, we had an expression like log kf prime upon kf is equal to Ea minus Ea prime upon 2.303 RT. And because a positive catalyst was lowering Ea to Ea prime, at a given temperature, Kf prime was more than Kf. This was for a catalyst. I can give you the energy profile as well. This was the energy profile. By catalyst, by default, I mean a positive catalyst. We will not talk about negative catalyst for the time being. This is what happened. This was Ea, this was Ea, and this is Ea prime. This is Ea prime. So because Ea prime is less than Ea, a catalyst, I told you, takes part in the reaction, changes the mechanism, changes the course of the reaction, alters the activated complex, lowers the activation energy, makes the process easier, and it starts happening at a faster rate at the same temperature. So a positive catalyst, Ea prime is less than Ea. How does it affect the equilibrium? Now this time, because the change of K, instead of Kf, I should write K here only. I've got used to equilibrium now, I'm sorry. This would be K prime upon K only, no Kf. This would be K prime upon K only. And now if it is Kf and Kb, now if it is Kf and Kb, now EAF minus EAF prime, and if it is for Kb, then EAB minus EAB prime is how Kf and Kb change. Now because the difference is the same. The difference for forward is the same as the difference for backward. This was EAB, and now this is EAB, and this is now EAB prime. So because the difference is the same, it favors, this is the difference, it favors forward and backward to the same extent, and if it favors backward and forward to the same extent, if EAF minus EAF prime is the same as EAB minus EAB prime, this means the change of Kf prime and Kb prime will be equal, and if the change in Kf prime and Kb prime is equal, then naturally Kf prime upon Kb prime will be the same as Kf upon Kb, which means Kc prime will be the same as Kc, Kc. So there is no change in the yield. Keep this in mind. A catalyst only increases the rate of the process. Catalyst does not changes the yield. Catalyst से रिएक्शन जल्दी होता है, कैटलिस्ट से रिएक्शन ज़्यादा नहीं होता है. कैटलिस्ट, द रोल ऑफ कैटलिस्ट इज इन द लोअरिंग ऑफ एक्टिवेशन एनर्जी. ये जो लोअरिंग होता है ये फॉरवर्ड और बैकवर्ड के लिए बराबर होता है. तो जितना फॉरवर्ड को मदद करता है उतना ही बैकवर्ड को मदद करता है. दिस इज सेम. सो Kf prime and Kb prime, they are both increase to the same extent, the ratio remains the same, and Kc remains the same. कैटलिस्ट से रिएक्शन जल्दी होता है, ज़्यादा नहीं होता है. एंडोथर्मिक में टेम्परेचर बढ़ाओ, रेट भी बढ़ेगा, यील्ड भी बढ़ेगा. एक्सोथर्मिक में टेम्परेचर बढ़ाओगे, रेट बढ़ेगा पर यील्ड कम जाएगा. यील्ड बढ़ाने के लिए टेम्परेचर कम करना पड़ेगा. उससे रेट थोड़ा कम होगा पर यील्ड बढ़ जाएगा, और यील्ड और रेट को बराबर रखने के लिए ऑप्टिमम टेम्परेचर पे काम करते हैं. सो दिस वाज अ लॉट ऑफ विजडम, ऑल द विजडम आई हैव गेन्ड ओवर ईयर्स एंड इज रेलेवेंट फॉर योर रिक्वायरमेंट. आई हैव ट्राइड टू पुट इट इन फॉर्म ऑफ दिस वीडियो. आई होप इट इज गोइंग टू हेल्प यू. इवेंचुअली एंडोथर्मिक में टेम्परेचर ज़्यादा रखने का, एक्सोथर्मिक में टेम्परेचर कम रखने का, यील्ड बढ़ाने के लिए. पर यह भी समझने का कि टेम्परेचर कोई प्रोसेस का एनिमी नहीं होता है. Exothermic में what goes wrong is EAB being more than EAF, the backward reaction is facilitated more than the forward reaction. So I hope all of this is going to help you in all type of problems involving the role of temperature and catalyst in all reactions, talking about them in one direction or in reversible reactions. This much for the time being. Thank you so much.